Hello everyone, welcome back to the course on Introduction to Multi-Agent Systems. This will be the final lecture on Introduction to Graphs basically. So let's get started. Okay, now in any multi-agent system we have a group of agents. For example, we see a system of drones here which are collectively trying to complete some objective, or even a group of people who are talking to each other can represent a multi-agent system. Now in general, agents and their interactions, as we have been discussing till now, can often be represented using graphs, where the agents become the vertices of the graph and an edge between any two nodes or vertices simply represents a communication between those two agents. And any finite graph which has a finite number of edges and vertices. Now, any finite graph consists of first a set of vertices V, a set of edges E, and using the set of edges and vertices, it is denoted as the graph G within brackets V and E. Also, in general, any graph can either be directed or undirected. When it is undirected, we say that whenever there is an edge between any two vertices or any two agents, then they are both communicating with each other. However, when the graph is actually a digraph, meaning a directed digraph, please remember that any edge I to j now means that I receives information from j, and the other way around does not follow from here. Okay. Now, the edges in a graph represents how the agents are connected to each other. Now, using the edges, we can actually define a few more attributes of any agent I. Let's get started. To begin with, let us say we have two vertices Vi and Vj. They are said to be adjacent to each other only when an edge exists between the two of them, as given here. Then, for every vertex Vi, we define a neighborhood or a set of neighbors n of Vi. So, what is n of Vi? It is simply the set of all of the vertices that Vi is adjacent to. So, note that here we are starting our discussion on undirected graphs. Some of these notions will change slightly when we move to directed graphs. Okay. The next attribute is that of a degree associated with a vertex Vi, and it simply refers to the number of neighbors that Vi has. So, let us quickly see an example. For the graph given here, let us try to fill in the blanks. Okay, so let us try to fill in the blanks. As we already know, this is the set of vertices and we have three edges here given as this. Now, let us look at the agent 1. We see that it has two edges and is adjacent to 2 and 4. Hence, its set of neighbors are simply this. And what is its degree? Degree is nothing but the number of neighbors that an agent has. So, here it says degree of the node 2. We see that node 2 has only one neighbor which is equal to 1. Hence, its degree is 1. Okay. Now, let us try to define these notions for the case of a digraph. Now, as I said before, the notions change slightly in the case of digraphs. Now, a digraph can have edges for any given vertex. It can have edges which are incoming to it or outgoing from it. Based on that, we define something that is known as an in neighbor. Now, given a vertex I, an in neighbor, it is simply the set of all neighbors of I that are connected to it by an incoming edge. So, we'll try to figure out some of these things for the graph shown on the left. In this graph, if you look at node 1, how many incoming edges does it have? It has only one incoming edge and it is from 4. Hence, its in neighbor is 4. Then, very easily, what is in degree? In degree is nothing but the number of in neighbors that it has. Hence, if you look at again the node 1, it has only one incoming edge, hence its degree is 1. Similar to in degree, we have something that is known as the out neighbor of I is a set which consists of all the neighbors of I which are connected with it via an outgoing edge. Again, let us see this through an example. Node number 1 has only one outgoing edge and it is to node number 2. Hence, it looks like this. And similarly, we can define the out degree associated with a vertex as nothing but the number of out neighbors a vertex has. Meaning, again, it has only one outgoing edge, this becomes equal to 1. Okay. Now, so far we have been talking about graphs like directed and undirected graphs which are not weighted in nature, but we talked it in one of the previous lectures that in fact graphs can also be weighted when every edge is actually associated with a certain weight. For example, if you are looking at a robotics problem, and maybe we are talking about some sensor via which two edges are connected with each other. For example, let us say if you have a robot which has an overhead camera or an onboard camera, then depending on the strength that the camera has, based on that we can assign a degree which would represent the quality of its measurement of its neighbor. That can be the edge weight. So, these notions again change very slightly when we make the digraphs weighted. So, I have reflected only the notions that get changed. Now, whenever the digraph becomes weighted, we say in degree is the sum of weights of all of the in neighbors of I, which would mean again if you look at node 1, we see that it has only one incoming edge. So, instead of this being equal to 1, we will actually write here the weight of that particular edge. Similarly, the notion of out degree becomes the sum of weights of all of the, this should be out neighbors of I. Again, if we look at node 1, we see here that it has two outgoing edges with weights 0.2 and 0.5. Hence, D out is equal to 0.5. Okay. Now, so far again we have been talking mostly about attributes which are associated with individual nodes in a graph. However, when we want to talk about the group in general, it becomes a bit more easy to talk about them in terms of matrices. Hence, it brings us to the first kind of matrix that will associate with the graph, which is known as a degree matrix. Let us look at this undirected graph. Then, the degree matrix of the graph first is a diagonal matrix. Then, the ith diagonal entry denoted as Di is nothing but the degree of node I. Meaning, okay, before we get to solving this example, so this is for an undirected graph. So, we know that a directed graph, in a directed graph every node has actually two kinds of degrees, the out degree and the in degree, meaning we will actually get two kinds of degree matrices associated with digraphs. So, this is denoted as D. When it comes to a directed graph, the first kind of a degree matrix could be D out, which is much like the degree matrix, is a diagonal matrix, but the ith entry of it is the out degree of node I. Similarly, we have the in degree matrix where the ith entry of it is nothing but the in degree of node I. Hence, what is the degree matrix of this graph? Again, let us see if it is correct, the expression that we have here. For node 1, it has 3 neighbors, and what is the sum of the weights of all of the neighbors? W1 plus W3 plus W4. So, this is correct. Similarly, for this, it has just one edge, hence it is W1, and the same way you can verify this for the other 2 nodes as well. Now, let us look at a digraph. Okay. Let us consider this digraph and try to calculate both the degree matrices associated with it. Now, the out degree matrix, let us start with that. So, 1, as you can see, it has 2 out neighbors. It has and the sum of their weights is W1 plus W4. The node 2, as you can see, does not have any out neighbors, hence this is 0, and same for 3, it is 0. And if we look at 4 again, it has 2 out neighbors, 1 and 3. So, D4 is equal to the sum of their weights, which is W2 plus W3. In a similar manner, we can compute, this should be D in. In a similar manner, we can compute the in degree matrix, which can be given here. So, please try it out yourself and see whether this is valid or not. Let us move to the next kind of matrix that we can associate with a graph. It is known as an adjacency matrix. So, an adjacency matrix simply represents the adjacency relation between every pair of nodes. What does that mean? If we have an undirected digraph, then the ijth entry of the adjacency matrix is equal to 1 only if there is an edge between I and j and is otherwise equal to 0. And when the graph becomes weighted, instead of writing 1, we replace it with the weight of that particular edge, meaning adjacency matrix has 0 entries whenever the corresponding I and j vertices do not share an edge, and otherwise the entry is non-zero. If it is a weighted graph, we substitute its weight there. So, again let us quickly calculate the adjacency for this matrix. So, we see 1 shares an edge with 2, 3 and 4, hence it becomes like this. And 2 shares an edge only with 1. So, it will have only one non-zero entry in this row, which is this. 3 has 2 edges to 1 and 4. And 4 again has 2 edges, hence this should become and 0. Okay. Again, so the notion follows directly to digraphs, and in this case it should look something like this. So, we can just quickly cross check some of the entries. Let us look at the entry 4 cross 3, meaning we should check if there is an edge from 4 to 3. We see that there indeed is an edge whose weight is equal to 2, which is substituted here. Similarly, if we look at the entry 2 cross 4, so we are looking for an edge from 2 to 4, we see that there does not exist any edge from 2 to 4, hence this entry is 0. So, is the adjacency matrix really applicable in any real world scenario? To answer that question, we will look at the DEAK-ROOT model. Now, just to quickly remind you of it, so we have discussed it in the previous lectures, but a very brief introduction. So, in the DEAK-ROOT setup, we are considering a group of n individuals who are interacting with each other about the same topic and trying to modify the opinions in a certain manner based on the interactions. As they interact with each other, to every person they talk to, they assign a certain trust index denoted as Aij. So, if they trust the individual, Aij is non-zero, meaning they talk to that person, and if they do not trust that person at all, then Aij is equal to 0, meaning they do not communicate with that person. So, again this notion is extremely similar to the adjacency, or rather it is exactly the same as it. Meaning when we try to model their opinion evolution, then suppose we say x of k is the n cross 1 opinion vector, which denotes the opinions of all of the agents in the group at some time instant k, then the update rule takes this form, where A matrix is nothing but the adjacency matrix associated with a graph. Hence, the adjacency matrix can actually be used to model distributed update rules within a group. Now, let us look at yet another kind of a matrix that we can associate with a graph, that is the incidence matrix. Now, incidence matrix is defined for directed graphs and gives us an idea of where an edge starts from and where it ends, meaning the incidence matrix B of G has, okay, first let us define something else. So, this is how we arrange the vertices in an incidence matrix if we are considering a group of n agents, and we have the set of edges represented here. Okay. Now, any ijth entry here is 1 if simply Vi. So, now we are trying to fill the value in a given row, say, then every row, as we can see here, is associated with an edge. So, we say that now if Vi is the head of the edge Ej, only then we assign +1 there. If it is the tail, we assign -1 there, and if it is not associated with the edge at all, it is 0. Let us try to understand this through an example. Let us try to construct the incidence matrix for this graph. So, we can see here that it will be a 4 cross 4 matrix because we have 4 edges and 4 vertices. Now, this is only for a reference so that we can easily write the matrix, but in general it is only sufficient to, of course, just write the matrix. So, let us see. Now, if you look at the first edge here, which is E1, we see that it starts at 1. So, we assign a +1 here, and it ends at 2, we assign -1 here, and rest of the entries become 0. For E2, it starts at 4, here, and ends at 3. So, this is what it looks like, and similarly E3 can be written in this manner, and E4 starts at 1 and ends at 3. So, this is how we can construct the incidence matrix associated with a digraph. Now, there is yet another kind of a matrix which is known as the Laplacian matrix. So, the Laplacian matrix is for any given digraph is defined using the adjacency matrix first of all, and the second using the D out matrix, which is the out degree matrix associated with a graph. Note that in the case of an undirected graph, since there is only one kind of a degree matrix, we write L is equal to just D minus A, which is the standard degree matrix. Interestingly, the Laplacian and the degree matrices can be related to each other through this expression. So, the Laplacian matrix, much like the adjacency matrix, is extremely useful, especially in applications in modeling human brain networks, power networks, water flow networks, and so on and so forth. Again, let us see a quick example. So, suppose we have this digraph, then let us try to calculate what the Laplacian will look like. So, first let us write the D out. So, there are 4 vertices, so it is going to be a 4 cross 4 matrix, and we see that this is 0.2 plus 0.3, 0.5, and the node 2 does not have any out neighbors, hence its out degree is 0, and node 3 similarly does not have any out neighbors, again its out degree is 0, and 4 has 2 out neighbors like 1. So, it is going to look like this. And let us draw the adjacency. We see that there are no outgoing edges from 2, hence this entire row becomes equal to 0. And the same holds for 3, and for 4 there are 2 outgoing edges. Hence, and 0.5. So, this is how we can calculate the Laplacian of a graph. Okay. Now, all of the matrices that we defined in today's lecture are extremely useful in modeling distributed protocols to govern the behaviors of a group. So, the first kind of matrix that we will talk about in the next lectures to come is the adjacency matrix, and how we can actually use it to devise a distributed protocol, and how exactly we can talk about the convergence properties associated with such a distributed protocol. Okay. So, with this we come to an end to this lecture. So, these are the references that we use for today's lecture. Thank you. I'll see you in the next lecture.